This is the final project for Physics 114 by Mikey Paula and Kellen Pope. Question 1. What is the consequence of preventing thread slippage against the eye bolt? So it's important to make sure that the thread is tight against the eye bolt, as shown in the picture, because otherwise the pendulum swing may change. So if the string starts sliding on the eye bolt as the ball swings, this may make the path of the swing uneven, and it'll lead to inaccurate measurements when using the video in LoggerPro. Question 2. What is the pivot point of the pendulum? The pivot point is the fixed point from which the object swings. So in this case, it is our metal ball attached to string. Question 3. Explain how to use the paper ruler to determine the pendulum release angle. So we know that the 20 centimeter ruler is a specific distance below the pivot point, 20 centimeters. And we can measure the distance from the vertical line to the point of release, as shown in the diagram that I have here. So we want to measure this distance x. And using our ruler, we measure this distance to be 5.5 centimeters or 0.055 meters. Question 4. What is the benefit of putting the paper ruler further down below the pivot point? Well, placing the ruler further below the pivot point allows for a greater swing arc to be measured, and these bigger measurements may lead to a more accurate values as a result. Question 5. What is your uncertainty in your measurement of the distance in step 4? So when measuring the distance from the pivot point to the ball center, the radius r, the tension of the string could affect this value. So for example, if we pulling hard on the string might lead to an incorrectly large measurement of the radius length, and in the same manner, measuring the string with lots of slack, so when the string is loose and not completely taut, it'll lead to an incorrectly small measurement. So we estimated that our uncertainty would be plus or minus 2 centimeters. Question 6. Why is a scale factor necessary? Well, a scale factor is necessary for LoggerPro to calculate and digitize all the measurements. So the scale provides numerical values in order for the program to make data. Question 7. What length might you choose to establish the scale factor for your data? We chose to use our 30 centimeter ruler that was in our video to establish the scale factor for our data. We knew the exact length of the ruler, and because it fits within the frame of the video, LoggerPro can use it to analyze data. Question 8. Free body diagram of the ball when it is at angle theta from the vertical. This is our free body diagram. Question 9. Write the Newton number 2 in the radial direction for the situation in question 8. This is our equation here. And I have it more clearly written out for the next question when you're asked to solve. The force of tension was determined to be 0.088 newtons. From our LoggerPro data, it determined our theta here to be 12.6 newtons, as shown here at this point in time, so at the beginning of the swing. So that's the data, that's the value that I used for that problem. Question 11, based on question 10, what angular position would you expect the thread tension to be greatest? The thread tension will be greatest at the bottom of the swing, or 0 degrees from the vertical. And at this point, the force of tension and force of gravity are working in opposite directions, as described by this formula, which is derived from the FBD. Same as this equation right here, essentially. Question 12. Use the conservation of mechanical energy to find the speed of the ball at its lowest point. We will need to assume the initial angle from the vertical. And this was done using this equation, solving for V final. We get the square root of 2 times GH, and we just plugged in values from the problem and determined that the speed at the bottom is 4.4 meters per second. 4.43 meters per second. Question 13. What is the speed of the ball at the highest point? Well, at the highest point of a swing, the speed of the ball is essentially 0. Our value here, 0.004 meters per second, is what Logger Pro determined the value to be in its data analysis. So this value right here. Question 14. Explain how Logger Pro finds x velocity and y velocity given x position and y position as a function of time. Logger Pro finds x velocity by analyzing the video to determine its x position and divides it by the time. And it does the same operation for determining y velocity. Analyzes the video to determine its y position and then dividing that value by the time. Expressed more clearly through this kind of equation. Question 15. Explain how you use Logger Pro to calculate speed. We created a new data column and entered for speed and entered this equation into the expression box. So question 16 is just elaborating on what I did for 15. So went to data, new calculated columns. This is a screenshot of that window. Entered this equation right here to calculate speed. And we essentially did the same thing for question 17. Explain how to use Logger Pro to calculate centripetal acceleration. So in new calculated parameters, we entered this formula here for centripetal acceleration, labeling, putting the correct titles for the labels in units. Question 18. Estimate the percent error in your determination of tension in the string at the lowest point of the ball. So again, errors could have come from inaccurate digitizing of video, incorrect measurements of string length, the radius, or the distance from the vertical. And like we said in the previous question, could have had an error of plus or minus 2 centimeters, and we calculated that to be percent error of 1.6%. And this is the calculation we did. Given that the string length could be 2 centimeters shorter, 2 centimeters longer, and this is our percent error calculation. Question 19. So this experiment is done on the Earth's moon. What is the value of tension at the lowest point, assuming the same release angle? So we use the conservation of mechanical energy equation to calculate the velocity of the ball at the bottom of the swing. It's shown by this equation. And the ball's position at the bottom of the string was used as the height in right here. And this value was also determined by looking at the Logger Pro data analysis chart for the ball at the lowest point. So here's the work that was done. So h was determined to be 1.007 from Logger Pro. Again, that value is right here. This is at the bottom of the arc swing. And then use that to plug in into the conservation of mechanical energy equation to get speed of 1.81 meters per second. So this is the speed of the ball at the bottom of the swing if the experiment was on the moon, and we plugged that into this equation and got the force of tension to be 0.044 newtons. So the 0.044 newtons force of tension is much smaller than what it would be on Earth. And that value at the bottom of the swing for the original experiment is 0.093 newtons, so a little less than half the force of tension on the Earth. And finally, question 20. The experiment is done on the Earth, but in an elevator accelerating straight up at 5 Gs. What is the thread tension in the ball at the lowest point, assuming the same releasing? Well, if you have the elevator accelerating at 5 Gs upward, you can write your FBD like this. So your force of tension is what you're solving for. You have the same force of gravity, which is just m times g, but then you also have m, the acceleration going upwards, so you have this force of 5 Gs. So this is actually the force of gravity in the opposite direction, so m times 5g. And then after plugging all these values, you determine the force of tension to actually be negative 0.348 newtons. So what this means is actually the ball, there is like no tension on the string, and the ball is actually moving up. I mean, the elevator is accelerating really fast, so it's almost like the ball is weightless. And finally, we just have screenshots of the graphs we produced in Logger Pro. So this is a tension versus theta graph, speed and acceleration over time, and I've referred to this already in the video, but this is our video analysis.